All right. So today we'll continue with the perturbation theory in the path integral formalism. So today, let's say it's part one of applying it and finding the final rules, and next time is part two. So both these lectures, this one and next, will be also a bit shorter because I want to emphasize the importance of this. So the one difference that we noted with respect to what we did in the operator formalism was the use of the Euclidean formulation. As we discussed at length, we used the Euclidean formulation in order to get rid of the problem of oscillatory path integrals or oscillatory integrals, and to get rid of boundary terms, and to better define the propagators. Then, specifically, we saw that the quantity to be calculated, the partition function, so-called because it was obtained from the statistical mechanics partition function in the limit of infinite temperature, and this corresponded to vacuum functional. And we saw that we obtained for it the so-called Dyson formula, which is a simple sort of reinterpretation of what we were doing. So calculating the transition amplitude in between vacuum states of the unperturbed theory with the insertion of these two things, exponent minus the interaction piece of the action and exponents of the source piece of the action. And then this gave us the path integral. So if we didn't have these things, it would be just the path integral of the free action minus S0. Sorry, 5. But now we also have these two things. So let's think of it this way. The path integral of E minus S0 plus S plus J phi, which is a quadratic piece, and then E minus S interaction, which is a higher order piece. And then we have seen that the non-interacting piece, the free part, which is just this one, we've calculated it to be normalization constant that we define as product of zeros times exponent 1/2 j dot delta dot j, and this we could put to 1. And in here, the propagator is the Euclidean propagator, which is uniquely defined. And it becomes, by analytic continuation, by Wick rotation, it becomes the final propagator. So that's the one that is used in calculations. All right, and finally, the last thing we did, we defined what we called was the Wick theorem for path integrals. The Wick theorem for path integrals was just a formula that seemed to completely calculate z of j. So we write this interaction piece. Now, here in principle, I could have chosen to have something more complicated, an SI that depends not only on phi's, but also perhaps derivatives and matrices and other things. But for simplicity, I just wrote E minus integral of a potential, where the argument of the potential, the field, is replaced by dBj. And then this object, so this thing where I replace phi by dBj, acts on this free partition function, z0 of j, that we've calculated. Okay? This one being e to 1/2 j dot delta dot j. Okay, so this was our Wick theorem. And as I said, this looks like it's solving completely the theory. It's a formula, a well-defined formula for the partition function. But in fact, this is only a formal expression because, well, first of all, this exponent with some derivative of some derivative operator is, of course, understood as just writing the form of the exponent as sum over 1 over n factorial, the exponent to power n. But even that is not well defined because we have several derivatives acting at the same point, for one. And the number two is that when we do this and we calculate the integrals, we will see that we get infinite results, so we have to deal with those in some way, otherwise this is meaningless. But the second point is, why do we call this the Wick theorem? I mean, it's not completely transparent that this is the same Wick theorem as in the operator formalism. So today the first thing we'll do a bunch of examples in great detail to convince ourselves that this is really the equivalent of the Wick theorem, and also to see how we actually calculated it. So the first example, we consider terms at zeroth order in the coupling. That is to say, since this potential has some coupling lambda, that is to say, I just ignore this piece, I just consider the free theory. So free theory. And from it, we derive the Green's functions. So we will be considering the endpoint functions, and this would mean at order lambda to the 0. So in general, I will call this the order lambda to the p term in Gn. Right? Okay. So let's start with n equal 1. So n equal 1, and first let's consider non-zero j. Then G1 0 j of x would be, remember now in Euclidean space, the formula for the endpoint function is without I, so I just take derivatives. So dd j of x of this z, now it's z0 of j, that is to say e to 1/2 j dot delta dot j, right? So when I take the first derivative, I take the derivative of exponent times the exponent times e to this, and the derivative of exponent is just delta dot j, right? 1/2 times 2, then delta dot j, e 1/2 j delta dot j. Okay? But we see now what happens. So I put this first at j equal to 0, at j non-zero, but of course the endpoint function is understood at j equal to 0. So j1, 0 of x is this thing at j equal to 0. And then we see this is proportional to j, so this will be 0. g1. And so we can easily generalize this argument now. So we could calculate, so j 2n plus 1 0 of x1, x2n plus 1, an odd number endpoint function, right? This would be d2n plus 1 dj x1 dj x2n plus 1 of z0 of j at j equal to 0. So I take an odd number of derivatives, right? But we see what happens if I take an even number of derivatives. I can have both hit this term and then get nothing. But then the next one that gives me the odd number of derivatives will necessarily act on the exponent and will bring down the delta dot j, right? So when I put j equal to 0, I will get 0. So this is now easily seen to be 0. Okay? So the 0th order term in the odd endpoint function vanishes just because the exponent in here is quadratic in j. So by taking an odd number of derivatives, I get down at least one remaining j. When I put j equal to 0, I get 0. Okay. Next, let's consider then the first non-zero case, the two-point function. So j g2 0 x1 x2. And let's consider this first at non-zero j. This is the second second order derivatives of z0, which is e to 1/2 j dot delta dot j. Right? So when I take the first derivative with respect to x2, and that will give me as before j dot delta x2 equal 1/2 j dot delta dot j. Right? So when I take this other derivative, can act either here or in the exponent. So I get delta of x1 x2. Right. Plus, the second possibility is taking another exponent now at x1 down. So j dot delta x2 and j dot delta x1. And everything still multiplied by e to the 1/2 j dot delta dot j. Okay? So now we see what happens. When I put j equal to 0, this is 1, and this vanishes, and we're left with the 0th order two-point function being just the propagator. So now in terms of our Feynman diagrams, which we had defined in the operator formula, and we can start to define again here. This will be just a line corresponding to the propagator connecting points x1 and x2. All right? Okay. Then the next non-trivial case would be n equal to 4, the 4-point function, since the 3-point function being odd is 0, as we said. All right. And well, I won't repeat this in this great detail. I'll put j equal to 0 from the beginning. So just say that this is b4, bj x1, bj x2, bj x3, bj x4 of this z0, and then j equal to 0, right? And the same thing continues to happen, right? So this was the second order derivative. Then the third order derivative, well, if it acts here, it will give 0, right? Then it can act here and remain something linear in J, or it could give one more exponent down, and then it could multiply either here or here, right? But then if I get a term with 3 j's, then the next time I get a derivative, this will give 0, right? And so at the third order derivative, I'm only interested in the terms linear, which have 2 deltas and a j. So when I take the fourth order derivatives, I get just 2 deltas. And then put j equal to 0, only these terms with 2 deltas remain. And of course, I can get all combinations, right? So from this, and then so one term is this, then times delta dot j at x3. When I take the second derivative, I get delta of x3, x4, right? But then I can have, for instance, the 2 derivatives acting on these 2 j's. So that gives me another delta f with x1, x3, and x2, x4, or reverse, x1, x3, and x2, x4. So all in all, I get all the possible permutations, right? All the possible pairings, which are 3 in number, right? x1, x2 with x3, x4, x1, x3 with x2, x4, and x1, x4 with x2, x3. Right. Okay. So now we can also write down the Feynman diagrams corresponding to this. Well, that's kind of easy. So I have these 4 external points, x1, x2, x3, x4. And the point is I can connect them pairwise in all possible ways, right? So I have this diagram. Plus this diagram, plus the cross diagram. Right? So these are the terms that I obtained from here. Okay? So it's easy to generalize then what happens to the general even point function at order 0. So on one hand, so the even point function, the odd point functions at order 0 are 0, and the even point functions I will have n products of deltas, right? With all possible parallels. So in terms of the diagrams, I will have this x1, x2, x2n, and I will have connections pairwise of all external points in all possible ways. So pairwise connections in all possible ways. Okay, so that's the result of the even point function at order 0. Okay. All right. So we finished, in fact, completely with the endpoint functions at 0 order in the coupling. Right. Now let's consider the first non-trivial order. So order lambda in z of j. So that means that from this exponent in here, I have to consider only the linear term. So instead of e minus this, I'll just write minus this. Specifically, let's consider v of phi lambda over g factorial phi cubed. So this would be the simplest case. Simplest case of interaction. So the free case is quadratic in fields, and the next case would be cubic. Though, of course, this is only a toy model, let's say, of only academic interest, because, of course, this potential is not bounded from below, right? Doesn't matter whether lambda is positive or negative. I always have a part either at minus infinity or plus infinity that goes arbitrarily negative, which means the theory is unstable. So this is unbounded from below. So it's unstable. It's not a good quantum theory. But we take it as an example of how to calculate things because it's the easiest. All right, so first order in lambda, as I said, means that this exponent, which would be this would be the exponent in the Vig theorem. But now I want to consider order lambda. So that means I only keep minus lambda integral keep this term. Okay? So, in order to calculate the endpoint functions, first I'll look at the partition function of z of j, and then I'll take derivatives on it. Then I'll take the derivatives corresponding to endpoint functions. I still have these derivatives to take. So I calculate z at order 1 in J. This, as I said, means the order of lambda. So this would be this operator, then acting on z0 of J, which is this thing, right? So now, so the first, let's do this one carefully, because as I pointed out, now the derivatives are at the same point and it's integrated over it. So minus lambda over 3 factorial integral dvx. Let's say I take 1, so I'm left with 2 derivatives. And then the result, as we said before, is j dot delta of x acting on this exponent. Right? Now, when I take the second derivative, I can again get down another term from the exponent, but I can also act in here. But if I act in here, remember this is the same x, so now I'll get delta of x and x. Right? So minus lambda over 3 factorial over dx, dj of x, delta of x and x, so that's singular already, plus j dot delta of x, j dot delta of x, and so finally, when I take the final derivative, when this acts here, I get nothing. It can act on the exponent, so I can get a delta xx times delta dot j of x. I can also do the same from this thing, so delta dot j of x cube I can get. And then I can act in here. So if I act in here, I can act either here or here, so I get a factor of 2, and then I get delta of x and x times j dot delta of x. But this is the same term as in here. So I had one term from getting down the derivative, from the exponent, and then 2 from acting here. So all in all, I get this, right? Next, so this is Z1, this is the full formula for Z1, for partition function at order lambda. And so now, if I want to calculate n1 functions, I want to take an additional n derivatives on this thing, and then put j equal to 0. But now what do we notice? In here, this is odd in j's, right? I have a term with 1j and a term with 3j's. So now the same argument as before. So if I take only one, it's just the result is the opposite in some sense. So if I take only one j derivative, I get this non-zero term. So I get something non-zero. But if I take 2j derivative, I get nothing. So this vanishes. Here I'm left with a j, and then from getting derivatives on the exponent, the same thing, right? So, so generalizing, you can see that now if I take an even number of derivatives, I will get 0, right? So that's because this Z1 of j is linear in j, whereas Z0 of j was quadratic in j. I mean, I shouldn't say even. I shouldn't say linear. It's odd in j. This is even powers times odd power. So this is odd in j. So an even number of derivatives gives 0. Okay? But then that means that the first non-zero term is actually the 0-point function. Sorry, the 1-point function. Right? So the 1-point function that's the first derivative of this thing at j equal to 0. And then, as we said, I mean, this part is irrelevant, it's higher order than j, but from this one I take derivative with respect to j, I get non-zero term. I get 3 delta xx times delta xx. So 3 delta xx, delta xx. X1, sorry. I should have called this x1. So now, in terms of Feynman diagrams, this would be what? So there's this external point x1, and then a point x that's integrated over. Right? So there's a delta between x and x1, and then a delta between x and x. Right? So that's my Feynman diagram. Next, let's consider the 3-point function. So that's the third derivative. Z1 j equal to 0. And then I get what? So if, so two more derivatives acting on this. So if I have only, if all derivatives act on this term, I get 0. But if all derivatives act on this term, I get something non-zero, right? And also non-zero is if I get down, so one derivative acting on exponent, I get down an exponent. And then I'm left with 1j from here and 1j from the exponent. So the 2 more derivatives can give me an additional term, right? So this would give minus lambda. And I should have, I was not careful with the overall factor. So the overall factor in here was minus lambda over 3 factorial. So when I multiply here with 3, I get minus lambda over 2. That's important to remember. So now I have minus lambda over 3 factorial. And then what? So if I act in here, the derivative with respect to x1, x2, and x3, the first time I get a 3 down from the power, then the second time I have second power, so I get a 2. So that kills the factorial. And then I'm left with just delta of xx1, so there's still the integral over x, delta of xx1, delta of xx2, delta of xx3, right? So that's one term.
The integral over x is the 1-point function as well.
I'm sorry?
The integral over...
Oh, yeah, sorry, thank you. Yeah. Yes, of course, because x is is not an external point, so it has to be integrated over. So I get this term, but then I also get terms, as I said, from this times getting one more down from the exponent, and then taking the derivatives on both, right? So what do I get here? So I have already, first of fact, I have already a 3, right? And then when I get the exponent, when I get down the exponent, I get j dot delta, so with 1. So overall, so this I can write, so I get the same minus lambda, but then only a factor of 3 to cancel the 3 here. So overall, I get a 1/2. And then, so I have, as I said, I have this times delta dot j. Delta dot j of, let's say, x1, right? And now I can act, so that's a possibility, delta dot jx1, but then if I act in here, I can get delta of xx2, and in here I'll get delta of x1, x3, but then I get all the other possibilities with x1, x2, x3 interchanged. So all in all, I'll get, so let's see, as I said in here, I'll get delta x, say, x2, or let me write this logically like this, delta of xx1, and then from the other delta x2, x3, and then the permutations, right? Delta of x2, delta of x1, x3, plus delta of xx3, delta of x1, x2. Right? All right, so this is the result for the 3-point function.
Isn't there a delta xx?
I'm sorry?
There's a propagator music.
Oh yeah, I forgot. Wait. Yeah, I forgot somewhere something. Yeah, delta is xx from here. Thank you. Right. So now let's see this in terms of Feynman diagrams. So this first term. So let's say I have this x1, x2, x3, and I also have a point x to be integrated over, right? So this first term has connections with all 3 points. So this is this, right? Then this term has a loop on itself, delta xx, and then a connection, and then 3 terms with connections from x to either x1 or x2 or x3. So this is 1 term, and then this, plus from x2 to x3, plus, let's say, this term, this, plus, say, x1, x2, x3, x with x3, x1, x2, right? And incidentally, I mean, we'll come back next time on it, but since we already know about symmetry factors from the operator formalism, we could find out what do we divide in here by. So the 1/2, you see, was for this diagram where I can flip this like this, right? So that was the factor of 2. Then this diagram I cannot flip anything, so this has no symmetry. This is a factor of 1. Here I can flip this again, so I have 1/2 overall in all terms, right? We'll come back to it next time, but yeah, it's kind of clear now that you know the symmetry factors. All right. All right. Now let's move to. So one could continue like this, but it's kind of clear what will happen. We've found enough examples. Now let's move to excuse me to the second order in lambda. Maybe starting here. Now let's start second order in lambda. So I want to act twice with the exponent in here, but so remember this was the exponent, right? So now I have to have it squared with 1/2, right? This would be, so this term came from E minus integral V, right? V in our case was lambda, and then ddj cubed, right? So exponent or second order in lambda means I take this exponent and with 1/2 factorial and the second power, right? So that's what I'm writing in here. 1/2 times the exponent squared. More precisely, let's call it x and y, so minus squared gives nothing, so 1/2. And let's say lambda over 3 factorial, integral dx, dj x cubed, then lambda over 3 factorial, integral ddy, djy cubed times this thing, right? So now let's consider specifically what we want to consider. So we could in principle consider higher point functions, but so okay, the first thing to note perhaps is I have 6 derivatives, right? And here I have even powers of j, right? So this thing, the result of this z2 of j will be even in j's, right? I have 6 derivatives, so that removes 6 j's out of an even power. So that will still be an even power, even in j, right? So that means that since again, when taking the endpoint function, I take nth derivative with respect to j, right? That means only even point functions will be non-zero. All point functions will be 0. So g2n plus 1, 2, x1, x2n plus 1 will be 0. So in principle, I can now look at non-trivial things. I can look at even point functions. And perhaps it would be worth looking at the 2-point function, but already at the 0-point function, we'll find something enough to satisfy us. So I'll actually consider g0, 2, right? And 0 means there's no x, right? So this is nothing but z2, this is z2, but at j equal to 0, right? Remember this thing, I take nth derivatives, and then I put j equal to 0. Any zeros of that doesn't matter, but I still need to put j equal to 0, right? So I'm looking at this partition function at j equal to 0, second order derivatives. So I want to calculate this formula at j equal to 0, right? So here I have all powers in j, all even powers in j, but here I have 6 derivatives. So that means I'm only interested in the term with 6 derivatives in this exponential, right? Any other term will give either 0 because of the derivatives, or I give 0 when I put j equal to 0, right? So the term I'm only interested here in the order j to the 6th term, right? That will be the only one non-zero, right? So the order to the j to the 6th term is the cube power of this exponent, because this is already quadratic in j. So that is 1 over 3 factorial times this 1/2 j dot of j cubed, right? So that's the only non-zero term. So let's write this. So j0, 2, which is z2 at j equal to 0. This is given by the derivatives acting on only this j to the 6th term, which is the cubic term. So let's write this in more detail. So 1 over 2 lambda over 3 factorial integral dx del j x cubed lambda over 3 factorial integral dy del jy cubed. And now from here, we said we keep only the cubic term being the exponent, so 1 over 3 factorial times and now I remember that this thing is a shorthand for two integrals, right, for the two arguments of delta. And so if I have 3 of this, so this thing to the power 3, I will have, for each term, I'll have 2 different integrals. So let me call this z1 until, oh no, z1, z2, z3, and z1 prime. That's what I call them. Prime, z2 prime, z3 prime. So these are the integration factors, and then for each one I have one half, so then 1 over 2 to the 3. I also have this overall 3. And then j of z1 delta z1 z1 prime, j of z2, j of z1 prime, sorry, and j of z2 delta z2 z2 prime, j of z2 prime, j of z3 delta z3 z3 prime, j of z3 prime. Okay, so that's my thing. And then, of course, at the end, I also need to put j equal to 0. I mean, it's not really relevant anymore because I already have 6 j's, but let's put it anyway. Okay, so now let's do the derivatives. First of all, this is lambda squared. Then let's see what can happen with the derivatives. Okay, so here I have 3 terms, 3 identical terms, and then I have 3 derivatives at each x and y. So one possibility is that I act with one derivative from here and one derivative from here on each side of delta, right? So one possibility would be, let's say, delta of x and y for each. So then this would be delta of x and y to the cube, right? Integral ddx dy, right? Remember that yeah, so these derivatives remove the integrals, right? And then I'm left with the argument of the derivative. Now, how many possibilities do I have for this? Well, each of these can act in 3 places, right? So that's a 3. But then the second one can act in 2 places. So that's a 3 factorial that kills this. So I have 3 factorial from this, and the same thing from this. I have 3 factorial from both, right? So that kills the 3 factorials in here. But then I also have, for each one, I have 2 possibilities. I can switch the roles of x and y, whether I act here or here. So that will kill for each also the 2 cubed. Right, so all in all, this comes with, so I will kill this, this, and this. But I'm still left with 2 and 3 factorial. Now there's another possibility that they mix. Right? So it's a possibility that, let's say, 2 of these things act both on the left and the right of the same guy. Right? how many possibilities like this there are? Well, if so one of these things acting in here, as I said, there are three possibilities. But then the second one, but then another one has to act in the same place, so that's one. But I have two choices in here of derivatives, so either one of the remaining two derivatives can act in here, right? And then the third derivative acts somewhere else, right? So let's say by doing so I get delta xx, right? And then I'm left with an x in one of them, and then with three y's. Well, there's only one possibility, right? This, that I have delta xy and the other delta yy, right? So that's the possibility. But now, now let's see. So now I have one out of each. One out of the three derivatives in here can act in here. So I have a factor of 3. And then in here I also have a factor of 2 for this. So this again gives 3 factorial, 3 factorial. But then finally I can interchange the role of x and y. So I have another factor of 2. Okay, so now I still have this, but now I cancel instead this. Wait, I'm still missing a 3 factorial. Yeah, where did I miss the last 3 factorials? Oh yeah, of course, because the first x that I chose was also the first x that I chose. I said I choose one of the three in here to act, but I also could choose one of these 3 terms to act on, and then the remaining one could act on 2 of these things. So that's also 3 times 2. Okay. All in all, this gives me this. All right. So this is the final result for the 2-point function. Now let's see the Feynman diagrams. Well, so there are no external points now, right? That now I have to just have these integrated points x and y. So this possibility is this one, right? And this possibility, again integrated over, is to have an xx and yy and xy, right? So that's, those are my Feynman diagrams. And again, knowing the symmetry factors, I can figure out why I have these denominators. So for this term, I have these 3 things, right? This gives me a 3 factorial. But then these points x and y are not external, they're integrated over, so I can flip them. I can also flip like this, the diagram. So that is times 2. So perhaps I should not put them because might confuse you. These are not external points. And in here, I have these things flipped like this and like this. And again, I can flip the whole diagram like this, exchanging the role of x and y. So I have overall 2 to the 3, right? Which is this fact. Okay? Good. All right. So these are the examples I wanted to give in order for you to realize that really the Wick theorem, even though it didn't look like it, it's actually the same Wick theorem as in the operator formula, because we get the same terms with the same Feynman diagrams in the same logic. Okay? But now there is a second form of the Wick theorem. Which we'll prove. And the form that we want to prove is where basically I replaced so in the first form we had two exponents, one with v where I replaced the argument by derivatives, and one with the free theory with its full arguments. Now I want to have derivatives on the free part. And then this acting on this term. Though since now this is a functional of j and not of phi, then I have to put phi equals 0 here. So to write this more explicitly so that there's no confusion of what it means. So the dot product here, remember, means integrals over the arguments. So dd phi of x and I should put, so the derivatives should act outside, so delta of x minus 1 with dd phi of x dd phi of y. Yeah, I could put it in the middle. I guess it's not confusing, but it's clear if I put it outside. So this is my derivative operator, and this acts on this thing. Alright? So that's the second form of the Wick theorem, and now we will try to prove it. And the proof amounts to a somewhat more general lemma called Coleman's lemma. And so instead of these particular applications, let me consider more general functions f of x, which is a vector space with n components, and g of y like this. So if I consider this, then f of ddx acting on g of x, which is our first form of the Wick theorem, right? So I understand this thing as f of x and this thing as g of x, right? Sorry, no, the first form was the other one. E minus integral V dj on e to 1/2 j dot delta j. Right, so this is f, this is g, sorry. Then this is the second form, that is to say g of d dy, right? X was j, and y is phi now, right? Acting on f of x e to the x dot y when y equal to 0, right? So now proving this, well, proving this can be done for examples. So because of the Fourier decomposition theorem, it's enough to act on exponentials. Right? Because that's what the Fourier decomposition theorem tells us, right? If I have a function f of x, I can write it as integral b and y to the I xy, then f of y. And so the x dependence is in this term, right? And then basically I call Iy in this notation A for one function and B for the other function, right? So by choosing these exponential functions, it's enough from the Fourier decomposition theorem to prove the lemma in general. And so now we just substitute this. So first for the left-hand side. So the left-hand side. Right, so f of x, f of d dx, g of x, is now what? E to the a dot d dx, and g of x is e to the dx, right? And this itself just means sum of n, 1 over n factorial, a dot d dx to the n, right? And then this thing here, sum over n, 1 over n factorial, d dot x to the n, right? But, okay, I don't even need to do this. The point is, if I take a derivative each time I take a derivative, I get a b, right? So I'll replace this with a dot b. So this is equal to sum over n, a dot b to the n, right? Times the same e to the b dot x, right? And now, you see, this is a separate thing. I can just take it outside, and this itself is just e to the a dot b, which means this is a e to the b dot x plus a, right? Which amounts to saying that this operator is actually the translation operator. Right? Fact which perhaps you know. So, but this is formal proof. And then the right hand side of this lemma is what? g of d dy f of x e to the x dot y at y equal to 0 is e to the dy is e to the b dot dy acting on f of x is e to the a dot x e to the x dot y equal to 0. And we just see here that this is the translation operator, right? This exponent e to the a dot dx acts as translation operator on x, right? Shifts x by a. So we apply the same thing here just for this translation operator. So this is translation operator on y by b, right? So I just translate this. So this is equal to, this is y independent, so it just stays the same. And this translates y by b, right? And now I put y equal to 0, right? So I get e to the x dot a plus b. Sorry. Oh, I did this wrongly. No, wait. What am I doing?
Oh, the right hand side should have been f of y e to the x y, right?
In the notes is f of y.
Oh, yeah. Of course. Yeah, it's f of y, right? Thank you. Yeah, otherwise it doesn't work. So f of y is a dot y e to the x dot y. So this is so this is now e to the y a plus x, right? And so now I translate y by b, so this is e to the y plus b a plus x at y equal to 0, which is e to the b a plus x, which is the same thing as here, right? All right. So we've proved this lemma, QED lemma, therefore QED Lich theorem. Right? Because as I said, well, we could write this more precisely. So x was j of x, and y was phi of x, and f was e minus integral v, and g was e to 1/2, let's call it like this, right? And so with this identification, we get exactly the theorem that we had before, right? So we see here we have e minus integral v of ddj, e to the 1/2 j dot delta dot j, and on the right hand side we have g, which is e to the 1/2, but now j is replaced with phi, so dd phi dot delta dot dd phi. That's this thing. And then f of y, that is integral e minus integral v, but of phi, y is phi, plus x dot y, which is j dot phi, right? And phi equals 0. So we've proven also the lemma, also the theorem, sorry, the lemma and the theorem. So now we have two ways of calculating endpoint functions in principle. But as before, once we have shown that we can actually obtain this, the result of this calculation from Feynman diagrams, we can forget about how we got there and just use Feynman diagrams. Okay, so now let me write for you the Feynman rules in X space. And let's consider the general polynomial potential. And so one observation, so when I did the operator formalism, we found a formula with a symmetry factor. And well, I reminded you how to get there from the path integral. But at this point, it's useful also to give a more algorithmic method. So algorithmic method means that I will consider all Feynman diagrams, even identical ones. And this is a useful one, well, in several cases. One, you have diagrams so complicated that you don't know how to calculate the symmetry factor. Maybe you want to get confused. And I can tell you it's useful in practical calculation to check yourself. The other one is, you want to find, so let's say S complicated. The other one is if you want to find all the Feynman diagrams. I mean, with a little bit of practice, you should be able to find all diagrams, you know, to kind of see how to write all Feynman diagrams after a few loops. But it's still a complicated business, and the algorithm method is still better if you can find how to generate all diagrams. And finally, to put on a computer. Right? Computer is difficult to program symmetries. It's much easier to just add things up. So next lecture we'll come back to the one with symmetry factor, but now we'll do this simplified form, you know, dumb form without thinking of anything. So for these rules, we would just write n external points. x1, xn. Each with a line sticking out. And then, see if I'm at order lambda to the n internal points to be integrated over. But they're with p lines sticking out. Right? So if I have an external line, let's say this is the next one, I write one line sticking out. And if I have an internal point, let's say x, then I write p lines sticking out, right? Yeah, I guess in my notes I put y1 and until yn. Right? And then once I do this, I connect all lines in all possible ways, giving me all the final diagrams. Connect all lines in all possible ways. So this gives me all final diagrams. But of course, if I do this, as I said, I consider also identical final diagrams. So this is just an algorithmic method. And then for the Feynman diagrams, I have to remember that what I'm doing here is Euclidean space. This is in Euclidean space. So for each diagram we saw in our example, so we had E minus integral V, so E minus lambda over P factorial times stuff. So when you expand it, we get minus lambda over P factorial to the power n, right? When we expand it to order lambda again, we got minus lambda over P factorial to the power n. Well, 1 over n factorial, right? So that means that for each vertex, we get a minus lambda factor. For each p-legged vertex, minus lambda. And then for each propagator, this delta of x and y, that was the Euclidean propagator. And then for each diagram, I have to still integrate over the internal legs. Yeah, I guess, how should I say? I still need these factors, so in my notes I put like this. So the point is I would still need to divide by p factorial, because now I'm counting different, identical diagrams as different, right? I have no symmetry factor at this point. So I have to put all of the thing that appears in front of the potential. So let me consider as in my notes the definition without 1 over p factorial in the potential. And then sum over all diagrams and n, meaning that Gn is sum over n, 1 over n factorial, sum over diagrams, f n. Right. F. Right. So to emphasize once again, I didn't put the 1 over p factorial in here, but as a result I will get, if there are no symmetries for the diagrams, I will get p factorial terms for each diagram. P factorial identical diagrams, right? So in this sum of diagrams, there would be a p factorial.
That's why you're putting the n factorial there.
No, this is n factorial, right? This is from expansion O. I'm looking at the term O lambda to the n in E minus integral V, right? So this is 1 of n factorial, and here is the order of the diagram, right? The order in lambda. But I mean, in this sum of the diagrams, there would be p factorial identical diagrams, I mean, of the order of p factorial identical diagrams, right? If there are no symmetry factors. And I deleted the p factorial from here simply to as a rule to remember minus lambda here. Maybe it's not so good, but all right. So let's do an example to see how we would do things. So I'll consider the 2-point function at order lambda so maybe let's say like this G2 1 of x1 x2, that is order lambda to 1 for the 2-point function. And the case is for p equal 4, so V is lambda by 4. Okay? All right. So first, we draw the external points, so we write the external points, so x1, x2. In this case, and we draw a line sticking out of each. Then we draw the internal points. In this case, there's only one, x. And we draw p lines, in this case 4, sticking out. And now it's a question of connecting all of these lines. I have 1, 2, 3, 4, 5, 6. Connecting these 6 lines pairwise in all possible ways. Right? Right, so one possibility is that I connect the external lines by themselves and these lines by themselves. Right? That's one possibility. But in how many ways can I do this? Well, x1 with x2, there's only one way to do it. But here, I've written, I mean, there are identical diagrams, so this is the factorial, almost factorial I told you about. But here, I connected the upper ones and the lower ones. But I could in principle connect also like this. That's another possibility. So one up with one low. Or crosswise, right? Crosswise meaning like this, and then like this, right? So these are the possibilities when I connect the external lines by themselves. But then I have, of course, also the possibility of connecting x1 with one of these, and then x2 also with one of these, right? So this is one possibility, right? But in here, I could, so here I wrote explicitly these 3, but here I have many more diagrams. The point is, we can count how many diagrams there are, because x1 is connected with one of 4, right? One of 4 points. And then x2 is connected with one of the remaining 3 points, right? and then the remaining 2 points are connected together. So there are 12 diagrams like this, so I obviously don't draw them, but you can draw them if you want. And it's perhaps also informative to write what would happen with a symmetry factor idea, right? So with a symmetry factor idea, I would say I have the symmetry of exchanging these two lines, and also these two lines, right? So this would be 2 to the 3, right? So I would have 4 factorial over 2 to the 3, right? Which is just 3 diagrams. Which are those 3 diagrams, right? And here I have just the symmetry of this thing changing like this, right? So I have just the symmetry factor of 2, which means I have 4 factorial over 2, which is 4 times 3 diagrams. So that's correct, right? Okay. Yeah, perhaps. I mean, it's kind of obvious, but let's write these things also. So this would be minus lambda integral ddx. I have 2 propagators, so delta xx squared, and then times delta of x1, x2. Right. This is this diagram, and these others are identical, so the same result. And this diagram would be, well, delta x1 x integral dx minus lambda, and then delta of x1 x, delta of x2 x, and delta xx. Right? Let's see, is there anything else I wanted to say here? I guess not. Yeah, so I guess that was everything I wanted to say today. Do you have any questions here? And again, do you have any questions about anything in the class? Because well, next week we'll have an exam. Oh, by the way, so it seems there's a saga. They finally have been able to get auditorium from instead of our classroom. So as I said in the email, in the last email, we'll have a class as usual next Monday, and the exam as usual on Wednesday. So we're going back to what was originally planned. There was no need to change anything. But for the exam, as I emphasize, is open book, so you can bring everything, any books, notes, my notes, anything you want. Just not the internet, because I don't put anything on the internet. So, and it's easily searchable also. The point about books and notes is that it's not easily searchable unless you know where to look. So, but the internet, you just like type something and so. Yeah.
I wanted to ask the same question that was asked last time about the finding diagram.
Okay, so that's one possibility. And you can make it to, you can define it to be that, right? That's just not what I wanted to mean it there, but yeah, if you want, you can integrate over the external points, over the momenta.
Okay, but the way you did it, you got both fixed external points and momentum.
Well, yeah, I mean that's the way that I would like to define it with external points, because you know I write the external points, right? So then if I write the external points, that can only mean x and y. But I also want it to be in momentum space, so I want to have momentum in external lines. Means this and p minus I p y. Right? But yeah, if you want to, you can define this by integration of momenta. I have no problem with that. But that would be just the x space. That would be just the x space two-point function written as a momentum integral. Right? You understand the difference? So the way I wrote it, it depends on momenta. Right? But if you integrate over momenta, it's just the x space one.
Right, but the way you wrote it, it also depends on the position.
Right, but that was just because I wanted to emphasize these points. Right? If I wanted to emphasize these points, it has to depend on these points. And then, but it depends only through these factors, nothing else. Right?
Okay, but it doesn't make sense to me to depend both on momenta and position.
Well, okay, it's one way people do it. I don't know. Maybe you don't like it, but it's kind of one standard way of defining things.
But what you're trying to define is the Fourier transform of the position space to point function.
Right, but again, if I would write just the Fourier transform, in principle I would not have the external points. Right?
Yeah, that's
As long as I put the external points, I mean that I need to put these factors here, which are the x and y defenders. But that's the only thing I put. Right? That's, well, maybe it's semantics, I don't know, but it's to me it's an important distinction.
well, I just don't understand what that diagram represents.
So the Fourier transform multiplied by the external points.
That's pretty much it, yeah. It's a standard way of defining things. I
So
don't
in
know.
order to get the x space propagator from this, just integrate over p.
That's right, yeah.
Not by putting the exponent, you know.
Yeah.
But to do the Fourier transform, don't you have to integrate over x and y?
I'm sorry?
This is the Fourier transform of the point function, two-point function in position space. But then don't you have to integrate over x and y to get the transform?
Well, yes, but again, so if you would integrate over x and y, you would obtain the momentum conservation, right? And remember, there were two different things I wanted to obtain to write a diagram with momentum conservation with delta function, or without delta function. That's without delta function is the one that's more traditional, right? If I would integrate over x and y, I would get conservation of momenta, right?
Well, but actually, if you do the Fourier transform of the each point function in position space, you don't get this explanation factors.
I'm sorry?
If you Fourier transform the propagator in position space, you don't get these explanations.
Yeah, that's why.
The
That's why, as I was saying, that this form is not the form with. So, if I would write P1 and P2, that would be the Fourier transform over the Fourier transform, so with these factors, but then I would get the 2 pi 4 delta 4 p1 plus p2, well, minus p2, right? But as I said, I don't want to obtain that. I want to obtain this g of p. Then I write it like this and with external lines. That's
But
all.
I don't think you'll get that, because the Fourier transform of the position space propagator is just the momentum space propagator. There is no exponential factor.
No, okay. All right, let's try to do this. Yes, perhaps let's start with just, no, let's write this, right? So, let me first write this like this with, so this would be integral dd d for z, delta xz, delta zz, delta zy, right? And I want to say that this is integral delta of p, delta of p1, delta of p, integral over p1, and I wanted to define this as with, let's see, so if momentum goes like this, e to the ipx minus I dy. So, let me see, so I write this as integral integral e to the I p ipx minus ipz delta integral dp. Delta of p, this integral d d for p tilde 2 pi 4 e minus I p tilde y plus I p z. Right? And then this thing would be, if I do the integral over z, this with this gives 2 pi to the 4 delta 4 of wait, something not, oh yeah, delta 4 of p tilde minus p. And then I'm left with integral d4p 2 pi 4 d4p tilde by 4 and then e to the ipx minus ip tilde y and delta of yeah, here I've got delta of p tilde, right? Oh, and this, yeah, this was integral p4 p1 2 pi 4. So I have z minus z, so 1 delta of p1. Okay. And p1 2 pi 4. And then delta of p, delta of p1, delta of p tilde. Oh, sorry, yeah, this was inside, right? And then I have this delta of p of minus p tilde, so I can put this, right? There's no difference. And so this result is this result, right? Right, so you see I have the 2 pi delta of p tilde minus p, which I want to get out. That's what I said. And the two integrations, which I also want to get out. And then I have this result. Okay? Is that clear now?
But you are integrating with p.
No, that's my point. I wanted these things to be depending on p, so I cannot integrate over p. Right? But I also want to take out this 2 pi delta, and I have the same p here, but I have the 2 pi delta out. I don't have the integrations, and then I'm left with this. Right? Again, maybe it's a semantics, but that's how I define things. Right? Anyway.
If you don't specify x and y, you don't have this.
Yeah, that was my point. That I put the points, the external points, then I have to specify x and y, then I have to put these factors.
But if you
Right.
leave it,
Yeah, if I leave it free, if I write it like this, I could understand this to mean the Fourier transform. Right? But my point is, I wanted to put these points and get rid of the delta, in which case this is what I get. Right? All right. Other questions about anything? Lecture 1, 2, 3. I don't know. Well, you'll have one more chance on Monday, but